Hello everyone, my name is Rohan Batni and my project is titled Mapping Unhealthy Diets and Predicting Obesity in Greater London. This project brings together ideas from spatial data science and public health. I used anonymized retail purchase data, actual grocery transactions to understand how dietary patterns vary across London and how these differences link to obesity rates. What makes this project unique is that instead of relying on surveys or questionnaires, which depend on what people say they eat, I use what they actually buy, their grocery transactions. This gives us a more objective, data driven picture of people's diet. And I am supervised by Shaila. Before diving into the methods, let me start with why this research is important. Poor diet is one of the biggest public health challenges we face. Diet related diseases like obesity, diabetes, and heart diseases cost the UK around 74 billion euros every year, both through healthcare costs and loss of productivity. However, these problems are not evenly spread across society. In London, obesity rates are far higher in boroughs like Newham, Tower Hamlets, and Croydon compared to wealthier areas like Kensington and Chelsea. This suggests that food environments, what people have access to and can afford, vary huge across the city. So this project focuses on identifying where these unhealthy dietary patterns occur, why they cluster, and how they relate to socio-economic factors. It's also about predicting. If you know which areas are at risk, we can help policymakers target interventions more effectively. One of the main strengths of this study is that it uses objective data, real grocery purchases, instead of relying on self reported dietary surveys, which are often biased due to memory lapses or social desirability. This study is guided by five main objectives. First is to build an unhealthiness index, a composite measure of dietary across London's neighborhood. Second one, to map and detect spatial clusters of unhealthy diets using spatial statistics like Moran-Sai and Lisa. Third is to predict adult obesity using both linear regression OLS model and the machine learning model called random forest. Fourth is to explore social equity, understanding how the diet obesity relationship changes across income levels. And finally, to run policy simulations, asking what if questions such as how obesity rates might change if people ate more fruits and vegetables or reduced sugar drink purchases. The overall goal is to bridge the gap between the data science and public health using advanced analytics to perform better urban health policies. This data comes from the Tesco Grocery 1.0 dataset released on Fixture 2019. It contains over 40 million anonymized grocery transactions from around 60,000 households aggregated by middle layer super output areas, which are MSOAs, each covering about 5,000 to 15,000 residents. We combine this dataset with spatial boundary files from the UK census and additional demographic data such as income, education, and population density. Next, to prepare the data, we filtered only Greater London MSOS. Missing values were imputed using the mean of each variable. All variables were normalized between 0 to 1 using min-max scaling. Finally, population and transaction adjustments were made so that data reflected average dietary behavior per resident rather than raw sales. This process ensured that the data was reliable, consistent, and comparable across all areas of the city. Next task is to build the unhealthiness index, which combines 8 dietary variables into one composite score. The formula takes the mean of all 8 energy from sugar, fat, energy density, sweets, sugar, soft drinks, and ready-made meals, and then subtract the positive ones, which are fruit and vegetable purchases and nutrient diversity. A higher UI means more unhealthy food purchases, while a lower UI means healthier consumption patterns. For example, a neighborhood where residents buys a lot of sugary snacks and ready-made meals, but a little fruit or vegetables will have a high unhealthiness index value. This gives us a simple yet powerful measure of dietary risks that can be compared spatially. In this map, we can see all the MSOAs which, to their corresponding unhealthiness value. Next comes spatial clustering. Once we have calculated the unhealthiness index for every MSOA, we examine how these scores were distributed across London. We applied K-means clustering to identify neighborhoods with similar dietary profiles and local indicators of spatial association (LISA) to find statistically significant hotspots, high-risk clusters, and cold spots, low-risk clusters. The results clearly showed that strong spatial clustering. The global Moran's I value was 0.31 with a p-value less than 0.001, confirming that unhealthy diets tends to group together. Hotspots were concentrated in East and Southern East London, especially Newham and Tower Hamlets, while cold spots were mostly in West London, such as Richmond and Hammersmith. This pattern mirrors income inequalities. Areas with high deprivation values have worse dietary risk. It's visually confirmation that place matters when it comes to public health. Next, we wanted to quantify how diet and socioeconomic factors predict obesity. We have used two models. One is ordinary least square regression, which assumes linear relationships. The other one is random forest regression, which handles complex and non-linear patterns in the model. Predictors included unhealthiness index, household income, education, income, deprivation, ethnic diversity, and population density. The dependent variable was adult obesity rate, the percentage of adults with BMI greater than 30. By comparing these two models, we could see how traditional statistical models perform compared to modern machine learning for health prediction. So next comes model performance and fit. The OLS model explained about 43% of the variance in obesity where R square value is equal to 0.3. But the random forest model improved on that, which has achieved a value of 0.81 for R square. And it also has lower error rates where RMSE value is almost equal to 2.3. This shows that relationship between diet, income, and obesity are non-linear, meaning the effect of one factor depends on the other. For example, unhealthy diets have a much stronger effect in the middle income areas than in lower income ones. Calibration plots confirm that the RF model predicted more accurately across all boroughs. It captured subtle variation in that the OLS model missed, especially in mixed income communities. Next, then we looked at which variables were most important in predicting obesity. The random forest variable important analysis revealed that the household income, education, and the unhealthiness index were the top three predictors. This means that while diet matters, socio-economic disadvantage magnifies its impact. Two areas may have similar eating patterns, but the poorer area will experience higher obesity rates due to additional stress, healthcare access issues, and lifestyle constraints. Mapping these areas side by side shows that obesity hotspots overlap with dietary hotspots and areas of deprivation, forming what's sometimes called a triple burden of equality. We divided all London neighborhoods into 10 income deprivation results from the least deprived, which means wealthiest, to the most deprived, which means poorest. We then examined how strongly unhealthy diet predicts obesity within each decile. If you look at the graph, from deciles 1 to 7, which means richer and almost up to middle class areas, unhealthy diets have a strong positive impact on obesity. But from deciles 8 to 10, which means the poorest areas, the relationship weakens dramatically. Which means for wealthier people, what they eat directly affects obesity. But for poorer communities, other factors like stress, income, limited healthcare access, and poor living conditions play a larger role. So diet alone does not explain obesity in deprived areas. There are deeper social inequalities at play. So finally, we have tested two hypothetical policy scenarios using the OLS model. If you consider a scenario A, suppose if we increase 20 percentage of fruit and vegetable purchases, then it's lead to a 1.9 percentage point drop in obesity. And in a scenario B, if we reduce 10 percentage in sugary drink purchases, then it's lead to a 0.5 percentage drop in obesity. This shows that encouraging fruit and vegetable consumption and reducing sugar drinks intake has a much greater impact on population. Because the model uses real purchase data, these simulations gives realistic evidence based insights for public health planners. These finding highlights the need for multifaceted public health strategies combining education, affordability, and access. So finally, this research demonstrates how big data can transform public health. Retail purchase data can provide near real-time insights into diet qualities, enabling authorities to identify problems areas before health crises emerge. Moreover, by integrating machine learning, spatial statistics, and socio-economic data, we can move towards predicting public health, which means identifying risk before it becomes disease. It also shows the value of interdisciplinary approaches combining computer science, geography, and health sciences to produce actionable knowledge. So yes, what we have learned. Unhealthy diets are geographically clustered and align closely with deprivation. Socioeconomic inequalities amplifies health risk. Machine learning models capture complex diet health patterns better than linear models, and policies focused on fruit and vegetable consumption yield the greatest benefits. So these are all the references which I have used for this entire report and my project. And all the analyses were conducted in R using tidyverse, SF, and SPDF and random forest packages. And here is the GitHub link code for my project. And thank you very much for listening. I hope this work demonstrates the power of data science and tackling real world health inequalities and inspires further research in this space.